So let's prove so-called Gauss's law. We are going to go with several steps. Okay, it's 3 steps in fact. Step 1. We're going to look at a special Gaussian surface or special net. Okay, this is a net surrounding a point charge. So the net we're going to use this time is a spherical net centered at the location of that single point charge. I want to show you first that for this particular configuration, in which a single point charge surrounded by a spherical Gaussian surface centered right here, I want to show you that the flux through this Gaussian surface is independent of the radius. Okay, it depends only on the charge inside. It is not a function of the radius of this net. Okay, so how do I show that? Well, this in fact is quite simple. So I'm going to go through that quickly. I'm going to call this the flux through this surface phi naught. This subscript 0 indicates that this has to do with a spherical Gaussian surface, so it's a special one. Okay, the radius is called r naught. Now, first of all, let's look at a little patch on the surface of that spherical Gaussian surface. And what's d phi naught? What's the flux through this little patch? E naught dot dA naught. Again, E naught is the electric field on the surface of this particular Gaussian surface, the spherical surface. E naught dot dA naught. dA naught is this little area. You'll notice that if the charge q is positive, okay, if the charge q is positive, then E naught and dA naught, they both point radially outwards, so they're in the same direction. So E naught dot dA naught is just equal to E naught times dA naught, right? Because the angle between them is 0. Okay, now next, we know what E naught is, don't we? Okay, it is KE. K can be written as 1 over 4 pi epsilon naught, as you saw in the textbook. So it's another way of expressing the fundamental constant K, 1 over 4 pi epsilon naught. Okay, and then times Q, right? Times the charge Q. That is the electric field, the magnitude. Don't forget to divide this by by r squared, r naught squared in our case. Okay, so that is the electric field, and then times dA naught. Now, this is d phi naught, the electric flux through this little patch. We're now going to integrate over the entire spherical Gaussian surface, so we are going to obtain phi naught. So what's phi naught equal to? Phi naught is the sum of d phi naught. So let's integrate. Now, this is the integrand, and you notice that throughout the entire spherical Gaussian surface, none of these things change really. 1 over 4 pi epsilon naught, Q, and even R naught. Nothing changes, right? Because this is a sphere, so R naught is the same throughout its surface, and therefore I can take this whole thing out, so it's Q over 4 pi R naught squared epsilon naught. Okay, this whole thing is a constant. And then what's left is the integration over dA naught. In other words, we're integrating over the entire sphere. In fact, I should really be more careful about symbols. Let me draw a little circle here indicating that this integral is over an enclosed surface with no holes on it. Okay, and so tell me, what is that equal to? The integration over the entire surface area of a sphere. Isn't that the surface area of the sphere itself? Isn't that equal to 4 pi R naught squared? Okay, and you can see that cancels with that 4 pi R naught squared. So what do you have left? You have left only Q over epsilon naught. That's it. So phi naught equals Q over epsilon naught. This is the special case. So you see, indeed, it is independent of the radius. Okay, so we proved our first step. If you have a spherical Gaussian surface surrounding the only single point charge, then you are going to get such a flux. But that is not what we need yet. We want something further. I want to show you that even if I change the shape of this Gaussian surface, so it is no longer a sphere centered right here, I want to show you that the flux still remains unchanged. The flux through that arbitrary surface is still equal to Q over epsilon naught, as long as that surface, that net, encloses the same amount of charge Q. Okay, so that is going to be our next step. Here comes step number 2. Now, step number 2 seems to be a lot more complicated than step number 1, because after all, we have to show it for an arbitrary case, right? So let's see how we can do that. I want to show, okay, here, first of all, this is our original net, which is just a sphere of radius r0, right? This is just radius r0. So from here to there, it's r0. From here to there. That was the surface before. Now, let me draw an arbitrary surface like that. Arbitrary surface. Okay, so the other side can whatever it wants. And I want to show you that the flux produced by this charge here, Q, through this surface and through that surface are the same. Okay? Now, the flux through this surface was called phi naught. Remember that? So the flux through that surface, we call it phi. I want to show that phi equals phi naught. So how do I show that? Okay. Now, imagine I draw a line coming out of the charge here. This line penetrates both surfaces. Okay? And in fact, this surface, I always use a subscript 0 to denote it. So this is the A naught, and over here it's the A. Because of the arbitrary nature of this new surface, the local orientation of dA may be totally different from the local orientation of the electric field produced by this charge, which is always that way. Okay, so this is always E. This is E. It's always radial, assuming Q is positive, but dA can be arbitrary. With this angle theta can be anything you want, depending on the shape of the surface. Unlike dA naught and E naught, they're always in the same direction. Okay, now, what is the flux through this part? What is d phi, which is E dot dA? This is E times dA times cosine theta. Okay, the problem is that dA can be anything and cosine theta can be anything. So how come I can simplify d phi and integrate so that phi equals phi naught? Well, let's be more careful. Let's blow up that part of the picture so I show it here. Now imagine this is the charge Q at the center. You draw a cone, okay? You know what a cone is, right? You draw a cone extending from this apex, which is the location of the charge. You draw a cone, and this cone will cut into both the spherical Gaussian surface and the new surface. Okay, so it's going to cut into both of them, and here is the area that it cuts out from the sphere, and here is this purple part is the area it cuts out of our new arbitrary Gaussian surface. Now, what I'm going to do now is I'm going to imagine there is a larger spherical surface centered at the same location, but with a radius from here to there rather are not. Okay, so here is a new Gaussian surface like this, and this new Gaussian surface, which is also spherical, when you draw this cone here, it's going to cut. This cone is going to cut out a new green surface like that, right? A new green surface like that. And the question is there any relationship between this new green surface and the purple surface, which belongs to the arbitrary Gaussian surface? Okay, this new green surface has an orientation like that because it's a sphere centered here, and that is both the orientation of the green surface and of the electric field. Okay, of the electric field, radially outward. So let's take a closer look at dA dot E, which is dA times cosine theta. Now let me ask you, what is the angle between this purple surface and this green surface? Well, the purple surface is perpendicular to dA, and the green surface is perpendicular to E, right? So what is the angle between these two surfaces? Isn't that the same angle theta, right? Because this purple surface is perpendicular to dA, and the green surface is perpendicular to E, right? So if this angle between D and E is theta, shouldn't the same angle appear between these two surfaces? So really, what is dA times cosine theta? you take that dA here, okay, this is dA, the purple surface, and you project this dA onto this larger sphere, what do you get? You get a shadow, right? And that shadow should have an area which is equal to this dA times what? Times cosine of the angle between this dA and the larger sphere. And that angle, of course, is just theta. So what do you think you're getting here? What's dA cosine theta now? Isn't that just the area of this green part? In other words, isn't that just the area cut out by the cone over the larger spherical surface? We call it dA prime. Okay, so what's dA prime again? dA prime basically just this green area. Okay, so that's the key step. With that, the next part is simple. Okay, so what's d phi? D phi really is just E times dA prime. Okay, now let's extend our calculation. So we're going to calculate E times dA prime, and that's from that you can see how the inverse square law plays a key role in our calculation. Okay, so d phi equals E dA prime. E is the electric field at the location. Okay, the electric field at the location here. We say this radius is r, not r naught. R naught is from here to there. Okay, this radius is r, and so therefore the electric field would be magnitude. Okay, 1 over 4 pi epsilon naught q over r squared. R squared. I'm going to use a red color for that squared. Inverse square law. Okay, I'm going to use a red color. So that's the electric field. And then multiply it by what? dA prime. What's dA prime again? dA prime is this little area. Okay, is this little area. dA prime. Now, dA prime, how is it related to dA? Well, more carefully, I should say, how is dA prime, which is this little green area, related to that area, which is dA naught? Okay, so this is dA naught. This is dA. This area, this distance from here to there is r naught. Okay, and from here to there is r. Now remember, both these green areas belong to a sphere. This is the smaller one, this is the larger one. Okay, so from the same cone, extending from the same cone, how is this area related to that area? Well, if the radius is doubled, okay, in other words, if r is twice as much as r naught, then this area should be what? 4 times as much as that area, right? Because, you know, a sphere twice the radius will have 4 times the area. So it is clear from geometry that dA over dA naught is equal to r squared over r naught squared. Remember that? Okay, this is geometry, and let me rewrite that here. dA prime. This should be dA prime. Okay, this should be dA prime. dA is the purple area. Okay, so dA prime over dA naught equals r squared over r naught squared. Okay, again, if you look at that diagram here, dA prime over this radius squared, r squared, should be equal to dA naught over r naught squared. Okay, this is from geometry. That's that. From this, I can now calculate. I can plug this into here, and then once I do that, I find that d phi equals to 1 over 4 pi epsilon naught, and there is a q here, 1 over r squared, again that squared is from Coulomb's law. I'm going to highlight it with a red color, and but dA prime is dA naught. dA prime equals dA naught over r naught squared times r squared. Okay, now that squared coming from here, I'm going to use a green color to highlight it. Okay, where does that red 2 come from? That is the inverse square law. Okay, inverse square law. What about that green one? That is due to geometry, because you know, as the radius grows, the area grows like radius squared. That is geometry. So this from physics, this from geometry. But guess what? They happen to cancel each other out, right? So this is a special feature of the inverse square law. Without this inverse square law, this is not 1 over r squared. 1 over r anything else? Can it possibly cancel with that 2 here, which is from geometry? No, it wouldn't. But now, for whatever reason, reasons we're not quite clear of yet, nature happens to pick an inverse square law, which neatly cancels. Which this r squared comes from geometry. Okay, so they cancel out. They cancel out. I really need to emphasize this. Okay, when can I emphasize this enough? This is from inverse square law. And that is from geometry. They just neatly cancel each other out. Then I get d phi equals to, since they do cancel out, q over 4 pi epsilon naught. Canceling out dA naught over r naught squared. Okay? Now, once I get that, you can see easily that this just equals d phi. In fact, if I show you a previous writing, you can see here that's how we calculate d phi. D phi naught, okay, d phi naught was equal to this, right? You see here, q over 4 pi epsilon naught r naught squared dA naught. It's the same as q over 4 pi epsilon naught dA naught r naught squared. So they're really the same. This really just equals d phi naught. As a matter of fact, if you integrate over the entire sphere r naught, okay, because now the integration is over a naught, not over a anymore, you can then recover the Gauss's law. Phi equals the integration of d phi, right? And that's the same as d phi naught. So it's q over 4 pi epsilon naught 1 over r naught squared, because r naught doesn't change as you integrate over the smaller sphere, and dA naught, as you integrate over the entire dA naught, you get the entire area of the smaller sphere, which is 4 pi r naught squared. These cancel out, and you're left with q over epsilon naught. The exact same result as we obtained for phi naught. So we showed that regardless of what shape the Gaussian sphere, the Gaussian net is, as long as it captures the same amount of charge, it doesn't have to be spherical. Okay, the flux, the electric flux over that Gaussian surface is always q over epsilon naught. Q is the single point charge that is captured, that is enclosed by the Gaussian surface. And that was the key step. After that, what's left is quite simple. Step number 3, arbitrary charge distribution. And that is, now we're going to look at the case where we have not just one charge, any number of charges. Okay, any number of charges enclosed by a Gaussian surface. What is the flux equal to? Well, let's see here. Suppose I have 3 charges, green one, red one, and blue one. Okay, Let's look at the Gaussian surface S2 first. This Gaussian surface encloses two charges, the red one, the green one, and there's also blue one outside of it. First of all, let's consider the contribution to the flux from the red one. Okay, it will give you Q. Let's say this is a Q1, Q2, and Q3. So this will give you Q1 over epsilon 1, right? The flux over the surface area S2 due to the red one, right? Now, the actual electric field is not just produced by the red one, it's also produced by the green one. So it's the actual electric field produced by both of them would be E1 plus E2. Okay, because of the superposition principle. But E1 produces this guy. What about E2? E2 will produce another contribution, Q2 over epsilon naught. Right? So what is the total flux then? You just add them up, right? This is produced by E1, this is produced by E2. Just add them up. Okay. And Q1 and Q2 are both enclosed by the surface. So therefore, the total flux would be simply Q1 plus Q2 divided by epsilon naught. And what's Q1 plus Q2? It is the total amount of charge enclosed by this Gaussian surface. So it's Q enclosed. You just add them all up, okay? Add them all up. Of course, you may wonder what happens. We have another charge, Q3 outside. Now, does Q3 change the electric flux on this surface? Of course it does, right? It changes the electric flux everywhere. Actually, it changes the electric field everywhere on the surface. But does it contribute to the net electric flux through the surface? Well, strangely enough, the answer is no. Because here, with a charge outside, let's see what happens. When you get a charge outside, here's the Gaussian surface. You get a charge outside. It is very different from the charge inside. Because when the charge is outside, look at how it contributes to the flux. Okay, it's going to produce electric field lines like that, right? You see here, you got a flux inward, and here you get a flux outward. Inward flux is negative, outward flux is positive. So these two fluxes cancel out. So do those two. So do those two, and so on. Okay, so when you have a charge outside, it will change the electric field everywhere, but it will not produce a net contribution to the flux. And therefore, this charge does not matter when it comes to electric flux for the surface S2. However, if we wish to consider the electric flux for S1, I must consider both contribution from these two and contribution from that one, because all of these three charges are now enclosed by our new Gaussian surface. So overall, what did we find? We find that for an arbitrary charge distribution, the following Gauss's law holds true. And it says that the electric flux over an arbitrarily shaped enclosed surface, which we call a Gaussian net or Gaussian surface, which is defined like this, okay? E dot dA over the surface A is always equal to 1 over epsilon naught times the sum of all the charges enclosed by the Gaussian surface. Okay, and this result once again has nothing to do with the actual shape and size of this Gaussian surface A, as long as all these charges are enclosed by this Gaussian surface. This is the famous Gauss's law. As you can see here, this Gauss's law was entirely derived from Coulomb's law. And what was the key step in our derivation? It was in step number 2, right? When we were able to cancel this r squared, right? So you go back here. That was the key step. This r squared cancel with that r squared. The red squared comes from the inverse square law, and the green one comes from geometry. And again, they cancel each other out, and that is how d phi has nothing to do with r, because if these two power factors are not the same, d phi will have to depend on r, because they cannot exactly cancel each other out, and we will not have such a clean Gauss's law. So Gauss's law is derived from Coulomb's law, and in fact it applies not only to the single Coulomb's law, it applies to any inverse squared law. Okay, it is a particular nature of inverse squared law. In fact, Coulomb's law was not the first inverse squared law we learned. We learned something earlier in Physics 1b. And do you recall what that was? That was the law of universal gravitation, right? It was also inverse squared. So you can imagine, you can also write something similar to this Gauss's law. You can write an equivalent of Gauss's law for the inverse squared nature of the gravitational field. And you will see interesting things can happen if you do that. Okay, so this is entirely derivable from any inverse squared law, in particular Coulomb's law. And why did we bother to write something like that? Coulomb's law itself looked a lot more simple than this. This, you know, it's a surface integral, right? I mean, Coulomb's law itself was just the force between 2 point charges. This looks a lot more complicated. So why do we bother to do that again? It is because with this new version, we have the freedom to pick any shape of the Gaussian net we want. And oftentimes that will lead to a simplification of the calculation of the electric field. So we're going to learn how we might do that, how we might choose a Gaussian surface to our advantage by exploiting the symmetry of the problem, so that this integral can be simplified in such a way that I can extract the electric field out of this integral, so that the calculation becomes very simple and I can find the electric field quickly without having to finish a nasty integral.